So we're back in 5-3, didn't get very far yesterday. You guys are trying the example, we'll get back to it in just 1 second as I check your homeworks. Get the trig by itself as best you can. If you need to transform stuff with properties or identities, you can, but eventually you're gonna have to use the unit circle no matter what. What's the very first thing you guys did to solve? Okay, you could do it 2 ways, minus or plus. Which way do we want to go? Minus? I heard this first, but technically it should work out both ways. No. Actually, the other class did do plus, to be honest. 1 equals, what's negative 1 cosine minus 1 cosine? Combine that. Got it. Solve for cosine by dividing both sides by? And you get cosine of x is equal to, you guys agree?
Yeah.
Am I done? No. But have I gotten the trig function alone?
Yeah.
Have I? Okay, eyes up here on the board. Remember, we're new notes, new section. New notes, new section. Is the trig alone? Yeah. But, what's the very last little note over here?
Use the unit circle.
Use the unit circle. So, how do I use the unit circle? Okay. Some of you guys were able to flip back, hopefully, to where I had you in your notes on the unit circle, and you were actually looking at it. This is a very rough rendition. Shh, don't judge too much. I have my 45s. I have my 30s, and my 60s, and my 30s, and my 60s, roughly. Okay. Cosine. When you look in the unit circle, you have these little x, y coordinates. Are the cosines the x's or the y's? Mm-hmm. So, which of the angles, if you're looking at your unit circle, hopefully you are, it'll make a lot more sense. Which of the angles had an x of negative 1/2? 2 pi over 3 did. Has 60 in the second quadrant. And 4 pi over 3. Now, Matt, can you ask your question that you asked me? Because some people were probably working and didn't hear it at the very beginning of the problem. You said...
does it have to be plus or minus 2 pi?
Before that. Sorry, before that. You said how many...
Oh, is it? Oh, that one.
Yeah, that one.
Thanks, guys.
What was that one?
How many answers do you want?
How many answers do I want? Because if you look at the unit circle, how many answers do we see right now? 2. But technically, if you were to use your calculator cosine inverse, it would have gotten, if you were in degree mode, which is easier to see, 120, so it would have only given you 1. And then there's another option of infinitely many. So, Matt, what did I answer that question with?
I haven't told you yet.
Ah, true. And then I also said, but if I didn't tell you to only give me certain, I probably want them all. So if I want them all, I want all answers. It just says solve. So solve for all possible solutions. Solve for all answers, which means infinitely many. All means all means all means all. So not just one, not just 2. PE is having way too much fun. But infinitely many. Question, how do I answer infinitely many? Why are there infinitely many? No restrictions. Meaning, to get to this angle, you can twirl as much as you want. Can you get to 2 pi over 3? Really quickly, really short, just one short rotation. But can you twirl a whole 360 and then decide to go there? Can you twirl a whole 720 and then, yeah. So how do you get all those answers? You say those are all 360 apart or 2 pi apart. And I need multiples of 2 pi. So plus 2 pi, plus 4 pi, plus 6 pi. That's what little n stands for. He's all integers, which are positives or negatives. Positive means adding. Negatives mean subtracting. So that encapsulates all the different possible angles that will end here, but what else do I need? All the possible ones that will end here. So I also need, I need you guys to see something. X equals, put a little comma, you're done. This is a very good, completely correct set of equations that shows the answer, but the back of the book will show it differently. Not for every single problem, but for this problem, it definitely will. And here's what the back of the book is going to show. Let me go ahead and get to single page. They're going to say there's a better way of writing it. Now, that kind of stinks because there's not always a better way. So sometimes it's going to look just like this, but they're going to say there's a better way of writing it, and this is their better way. Once again, our first way isn't wrong. It's totally right. But they're going to say probably the following, which is also right. Question, is it the same?
Yeah.
How?
So it could be whether it's
How many positions do I need to get to? How many different terminal sides? All of them that end in how many different places? 2. Well, how does he get 2 places? You can go up 2 pi over 3, or you can go back 2 pi over 3. Question, does this formula get the same 2 positions in all their coterminals? Cheaters! I know. They just thought it looked nicer, and it kind of does. Doesn't it look a lot easier? Like you're going to think that your answer is wrong? Yeah, but your answer's not wrong. Okay? You can answer with the back of the book version. You can also answer with yours. What you need to check is, do they both express or explain or show the exact same 2 positions or the exact same answers in all their coterminals? As long as they do, you're fine. Sound good? Let me go back real quick to that picture that we skipped that you don't have to write down in your notes. Okay, this one. The whole point of this page is how to find and visualize solutions, aka when you get to something tricky, not even tricky, when you do all the work and you get to trig function equal to number, whether it's cosine, like this one, whether it's cosine of x equal to -1/2, whether it's like bell work yesterday, sine of x equals 1/2, or the beginning of notes, sine of x equals -1/2. When you get there, there's 2 different ways of thinking about it. I think one way is easier and the other one's harder. You guys might agree or might disagree. Technically, yesterday, bell work, I had you think about the unit circle, and I had you think about which angles for sine of x equals 1/2, which angles have a y of 1/2, which pi over 6 did, and 5 pi over 6 did. So you could have looked in the unit circle or from memory and said, hey, there's an angle that has y of 1/2. There we go. And also over here, here's another angle that has y is 1/2. So unit circle, that's what we're doing. We're looking in the actual coordinates and trying to pick out the right answers. Now, up here from the sinusoid, we know this is a sine curve because it starts in the middle, goes up, goes back down, ends at 2 pi, okay? We could technically graph y1 to be sine, y2 to be 1/2, and we could find little intersections, which in degrees are going to give us nice numbers, and radians are going to give us really nasty decimals. And those technically will be answers as well. And when we add 2 pi, we're just going to the exact same spot, but on another wave. When we add 2 pi, we're just going the exact same spot, but on another wave. And so when we add those 2 pi n's, when we add 2 pi times 2, when n is 2, we would just go to the next point on the next curve. So that's how the plus 2 pi n works. You could subtract 2 pi n, the exact same place on a different curve. For some people, it's easier to visualize the sinusoid, but in my mind, I think it's harder. I love the unit circle, or I at least appreciate it more. I think it's easier. But I just wanted to show you both ways, plus every now and then the book might have you use your calculator to graph a sinusoid or graph an equation and then graph the other side and find the intersections. It is a way of solving. The unit circle is better because you can do it without your calculator. So I wanted to show you this to you, but you don't necessarily need to write anything down. Just the idea is you could use a sinusoid to solve and find intersections with one side of the equation and the other. Or you could look in the unit circle because you know sine is y and find the right places. Let's go back. Let's look at another one. Now, the problem before that we just looked at, the goal was, I'm going to quickly go back. The goal was to get cosine alone, which we were able to do by saying, hey, it's a like term with the other side, and I was able to combine like terms. -1 minus 1 is -2. Is this one easier or harder? Give me that one. Harder. Because, do I only have one trig function or do I have more than one? How many do I need to solve? I need just one. So hold on. Can you guys go look at the steps real quick that we wrote down? Step 1 said, get the trig function alone. Or if you can't, try to use identities and transform stuff. And eventually we have to use the unit circle. Can we get one trig function all by itself? No. We can't get all the trig functions just by themselves. Well, can we transform them? Sine squared equals 1 minus cosine squared. Some people are able to say that because they've been studying their formulas. Good thing is you don't have to have them memorized by tomorrow. But you strictly, for one part of the test that's coming in a couple weeks, one part is just going to be, do you have your formulas memorized? So, if you haven't yet, maybe not for tomorrow because tomorrow it's just on problems. But if I were you, I would start making flashcards. Your brain, if they know the formulas, your brain can answer questions with formulas and it makes it a lot easier. So right now you can be flipping back and forth. Sine squared is 1 minus cosine squared. We could have also made cosine squared of x 1 minus sine squared. But since someone saw the sine squared and changed it right away, this is good. How do we keep solving? We're trying to get them all together on one side. What we do to one side, we do to the. When I carry down the 1, he's right there. What happens on the right? 3 cosine squared plus, oh, how many cosine squareds is this one? Understood, 1 will be. Are we getting the trig condensed in one spot? Good. We have to keep on getting the trig by itself. So, kiddos, come on, math. What do we do? Divide by 4 on one side, divide by 4 on the other. Good. Some of you might like it a little bit better. Let me zoom out. Might like it a little bit better if we get cosine squared alone on the left. Now hold on, wait a minute. We want to get just cosine of x alone. What do we have to do to both sides? Square root. Matthew, go ahead.
For when we added cosine squared x to both sides, is it legal to just throw 3 cosine squared x just plus cosine squared x and then divide by 3 on both sides?
No, because remember when you divide one thing by 3, I'd have to divide that by 3 and this by 3 all at once. Yeah, so we want to condense it. We want to combine as much as possible first. Noah.
Could we have square root?
We couldn't have here because there is no square root of 1 minus cosine. Well, I guess we could have square rooted up here. That's true.
No, but before dividing.
Yes, we could have. Yeah, we could have. But even if we didn't square root earlier, we have to square root now, right? Because we have to get rid of that squared. So when we square both sides, square root one side, square root the other. Now hold on. When we put in a square root, unless there's something special going on, what do we always have to do with signs? include both
plus
plus or minus. So when I put in the squared, I apologize, the square root, I didn't finish my sentence. When we put in the square root, it's going to be plus or minus. Now, some of you are looking at that and saying, wait, we have to go to the unit circle? That's not in the unit circle. Is it though? We can split up every time we have a fraction. We can split up numerator, denominator. Square root at the top, square root at the bottom. What is the square root of 1? 1. What is the square root of 4? 2. Is that in the unit circle? Yes. If you need to, right now, flip back to your unit circle. If you don't know it very well, you're looking for any angles where cosine is equal to positive or negative 1/2. See if I can make this at least a little bit better. It's one of the best ones yet. I'm just going to copy him. Okay. Question. What angles did you guys find? Where is cosine 1/2? 60. 120. All of the 60-degree ones, right? So this one I think is pi over 3, right?
Yeah.
2 pi over 3. What are the other ones?
4 pi over 3.
And here's the dealio. We need, Matt, did they tell us 1, 2, or did they not really tell us so they mean all?
They didn't tell us, so we have to do one.
Okay, so all. Infinitely many. We could technically take the 2 pi over 3 and add 2 pi n. Oops, I skipped one. I skipped pi over 3. And we can take how many different positions in the unit circle? How many different locations? 4. I could take each and every one, say all of his coterminals and all of his coterminals. Comma, comma, comma. X equals. Is this right?
Yes.
Definitely. Do you think maybe there's a better way?
Yes.
Huh? Pick the first two? How could we just pick the first two? What do you think, Noah? Plus or minus, just like the last one. Remember the cosine, how you can go up and down? And they kind of shortened it? Well, kiddos, pi over 3, could you go up pi over 3 to get there?
Yes.
Could you go down pi over 3 to get there?
Yes.
So technically, we could have said this. The back of the book probably would say this a different way. They would say x equals plus or minus pi over 3, which is technically the exact same thing as these two. It'll hit location 1 and it'll hit location 4, basically. And then they also, well, they have to write a second equation and put what instead, or in addition. Yeah, they have to also say. So that's how they would shorten it. That's how they would make it look nicer. They both mean the exact same thing. Because plus or minus 2 pi over 3, like we already saw, hits location 2 and location 3. So this one says, hey, look, 1, 2, 3, 4 different places. And this one says, I know, but I can write it nicer. 1, 2, 3, 4. Okay. What was different in this one? What did we have to start with?
Transforming.
We had to start by using our skills from 5.1, 5.2. We had to transform before we could ever solve. So maybe one reason for learning 5.1, 5.2 isn't just to figure out, like, hey, let's do puzzles with trig, but also, hey, let's make it possible to solve really harder things in the future. Can we do one more? Remember, we don't have to finish today. You don't have to finish today. We're just trying to get some examples, and tomorrow after the quiz, we'll do some other examples, harder examples to help you finish on it. Don't forget math. I know there's yucky trig stuff, but don't forget the math. When you're looking at this problem, do you need to factor anything? Or is it already factored? It's already factored. What happens when you have factors equal to 0 and you need to solve? This happens every time you factor a quadratic and you're trying to find the zeros. What would the math have you do?
Just take the ones in the parentheses.
Take the ones in the parentheses, kind of. Take each one, I would say, separately. We're used to seeing two sets of parentheses. There isn't one, but technically, he's still a factor. When you have two quantities, two expressions being multiplied equal to 0, either one of them is 0, or the other one is. So we can't even do anything on this one unless we figure out the math, which says, oh, hey, factors equal to 0, set each one equal to 0. Math.
Is it cosine parentheses x plus 1 in parentheses, or is it just cosine x?
Since they don't show it to you, you have to assume, since there's nothing shown, that it's just parentheses around that one. Yeah, good question. It would have to show parentheses for me to bring anything else in. Now, kiddos, I'm going to do some pretty quick math over here. Get cosine by itself. And over here. Get cosine by itself. It already is. Will stink. Over here. This one hopefully rings some bells. Because we've already been talking about quite a bit today. When does cosine equal 1/2? So I could mark this. Oh, thank you, negative 1/2. The x, negative 1/2 at 2 pi over 3. And third quadrant, right? 4 pi over 3. Okay, so hold on. There are two answers. Uh-oh. We have this whole interval thing. What do we do with that? We also have to figure out, wait a minute. When does cosine equal 0? Okay, when does x equal 0? Isn't this where the x is 0? 0, 1. So that'd be pi over 2 and 3 pi over 2. So first of all, I have all these different answers. Second of all, I'm not allowed to give infinitely many. Well, then what do we do? Question. Does 2 pi over 3 fit between negative pi and negative 1 pi and 1 pi? Yes. Why? How do we think about it? 2 pi over 3 is the same thing as how much of a pi? 2/3, right? 2 pi over 3, isn't that 2/3? If you were to think of, remember our calzone? Think about half of a circle as being 1 pi. This isn't quite 1 pi, right? Yet, anyway. You think about it this way. From 0 to pi, like on a number line, 0 to pi would cover these angles. Negative pi to 0 would cover these angles. I'm allowed to look at positive pi and negative pi. So as I just go through positive pi, can I hit 2 pi over 3? Yeah, so that's an answer. 2 pi over 3, good. But question, can I go past pi to get 4 pi over 3? No. But I can go down, and when I go down, what distance would it take for me in order to be able to get to 4 pi over 3? What is that angle?
Negative.
So I have plus or minus, positive and negative 2 pi over 3. Those are two answers that fit in this interval from this side. Well, what would I do over here? Positive pi over 2, is that good? As I go? Yeah, he's good. But can I keep going to 3 pi over 2? But what can I do? Go back, so what would the other one be? plus or minus. Now, there is one little thing. If you guys get to this in homework tonight, you might want to stop. We still haven't dealt with this little 2. We'll have to talk about him tomorrow after the quiz. Kiddos, look at homework problems. The stuff that's in there. Look at examples from 5.1 and 5.2. That's what's going to be covered on the quiz tomorrow. Maybe not exactly, but close. Come ready. Okay, guys.